The San Francisco Estuary is the largest on the Pacific coast of the Americas, defined by a severe and dangerous geographic contradiction. It begins with a deep, narrow entrance at the Golden Gate that immediately opens into a vast, sprawling interior bay. As Map 1 shows, this geography creates an extreme depth disparity. The entrance plunges to 356 feet deep, yet two-thirds of the bay's total interior is less than 18 feet deep. Massive, deep draft vessels, like this Chevron oil tanker, must navigate this shallow environment while confined to narrow, artificially dredged channels. In a high-risk environment with these tolerances, a single human error or mechanical failure leads to catastrophic economic and environmental consequences. Pilot skill alone cannot guarantee safety. Survival in this estuary requires a rigid matrix of physical and administrative controls, known as the Harbor Safety Plan. Understanding this waterway requires looking at it not as a natural body of water, but as a complex, highly regulated mechanical system. The system's constraints start at the Golden Gate, a hydrodynamic choke point funneling immense tidal volumes. During tidal extremes, the ebb current forces water out of the bay at blistering speeds, reaching up to 6.5 knots. These extreme currents generate dangerous, unpredictable eddies between Lime Point and Fort Point. Above the water, the summer fog cycle, driven by the Pacific high-pressure system, adds a second major environmental navigation hazard. The physics of the inversion layer, warm oceanic air moving over cold coastal upwelling, creates the thick fog seen here, obscuring the Golden Gate Bridge. This advection fog is pulled through the gate at 14 knots, rapidly reducing main channel visibility to zero. Mariners cannot rely on visual navigation alone. They require a constant stream of real-time environmental data to survive these rapid changes. The Physical Oceanographic Real-Time System, or PORTS, provides the essential sensor network tracking these parameters. Because the bay's physical forces are extreme and volatile, safe transit decisions rely entirely on real-time technological monitoring. Even with clear data, the central bay floor hides significant bathymentic hazards just below the surface. The submerged Harding, Shag, and Arch rocks are especially dangerous, peaking at just 33 to 36 feet below the water level. Deep draft vessels drawing more than 45 feet are trapped in narrow lanes passing directly over these peaks. The Army Corps of Engineers determined that structural removal of these rocks was unnecessary only because of the strict operational controls in place. The primary mathematical safeguard preventing groundings is a metric called under-keel clearance. This diagram demonstrates the exact formula for offshore approaches. Vessels must maintain a clearance equal to 10% of their total draft. In bay, the margin tightens further. Vessels must maintain a strict minimum of 2 feet of clearance. Calculating this tiny margin requires precise ports tidal data, as moving ships experience dynamic forces like squat and list, lowering their profile in the water. When the physical depth cannot be changed, safety is engineered through uncompromising mathematical margins between the hull and the bedrock. Beyond depth, the system must manage cognitive and physical congestion, coordinating roughly 400 daily vessel movements. Vessel Traffic Service San Francisco acts as the central control architecture managing this traffic. VTS requires strict VHF handoffs for all vessels, shifting from Channel 12 offshore to Channel 14 once in bay. Power-driven vessels over 1,600 gross tons are subject to a hard-capped speed limit of 15 knots. This speed limit minimizes stopping distances and destructive wake impacts within the narrow channels. Rules further mandate engine readiness. Engines must remain in control modes, ready for an immediate maneuver. They are never locked in unreactive states. Extreme pinch points, such as these narrow bridge spans, are designated as regulated navigation areas. In the Benicia-Martinez RNA, rules require direct ship-to-bridge communications and prohibit transits entirely if visibility drops below 1,000 yards. To provide artificial radar targeting during dense fog, raycons are mounted directly on these bridge spans. VTS acts as the cognitive traffic cop, converting a chaotic, low-visibility waterway into a strictly orderly, regulated machine. The ultimate failure occurs when a massive tanker loses steering or power while trapped in a narrow channel. The 1997 Tug Escort Regulations established physics-based match-in matrices for tugs and tankers following the results of the comprehensive Gloston study. These matrices use a single failure standard, providing force to arrest a tanker experiencing machinery failure. Calculations rely on a stern static bollard pull, the backward force countering the tanker's mass. This keeps the crippled vessel within a tactical area, stopping it before striking rock. Under this strict regulatory framework, these massive tug escorts actively function as precisely mathematically calculated multi-ton emergency brakes. Safe navigation in the San Francisco estuary is the product of an engineered equilibrium, never a matter of chance. Extreme tidal currents, hidden rocky peaks, and sudden zero-visibility fog define the baseline physical threats. The harbor safety plan counteracts these threats through overlapping layers: ports sensor data, VTS routing, and tug escort tactical boundaries. This system integrates under-keel clearance math, traffic control constraints, and the brute force physics of emergency tug assistance. The final philosophy of the estuary is clear: commercial efficiency must always be subordinated to systemic redundancy. By engineering absolute constraints around extreme physical hazards, the estuary protects both its vital economic arteries